This is an application of the Force Toolkit to magic pulleys and pulley systems. So we have to remember all of the steps of our Force Toolkit because we will apply them to this new scenario. In this problem, it says to derive the acceleration, assuming a coefficient of friction of mu sub k between the table and the M3 block. Determine the tension in the string. So step 1 is for us to determine what the accelerated system is. Now remember, we're going to do this a little differently. Instead of looking at one object at a time, we're going to look at the system. In this case, both M3 and M5. So our system is both M3 and M5. Step 2 is to determine our coordinate system. Our coordinate system goes along the line of action, along the line of the string. So anything going to the right along this string is positive. Anything going back over to the left would be considered negative. So this direction is positive, and anything in that direction is negative. In step 3, what we will do is we will look at a force diagram, or the force diagrams for these blocks. So for block M3, we have the normal force on block 3 from the surface pushing up onto the block. We've got the force of tension pulling to the right along the surface. We've got the force due to gravity straight down on the block. We've got kinetic frictional force. That's assuming our object is going to move in that direction. And like we said, we have the normal force. Our motion map would look like this, in that we would expect the object to move up the incline with increasing velocity, so the acceleration should be up along the incline. Our force diagram for the M5 block would look like this, with the force of tension pulling upward like that, and the force due to gravity on it pulling downward. Our motion map would assume that the object starts at rest and increases in velocity on the way down. Because the velocity arrows are increasing, the change in velocity, which is acceleration, is pointing in the same direction, in this case downward. Then what we'll do is we'll rotate our axis for the M3 block. And the reason we're doing this is so that we have a fewer number of off-axis forces. Now, in this case, we only have one off-axis force, whereas before, we had 3 off-axis forces. We will also include the components to that off-axis force, M3G. Since this is the angle that is the same as that angle, this side is the adjacent side, so it's M3G cosine theta. The opposite side is the sine component, M3G sine theta. Then we write out Newton's second law, the sum of the forces equals the mass times acceleration. Then step 5 is to plug in from all of our forces from our force diagram along the line of action. So let's look at our forces, all of our forces along that line of action. So we've got M5G, which is pulling down in that direction right there. We've got the force of tension on the 5 kilogram block, or M5 I should say, pulling upward, the force of tension there. We've got this force of tension on the M3 block pulling up and to the right. We've got the kinetic frictional force pulling to the left. And finally, along our line of action, which would be in this direction, we would have the sine component of M3G. So we have a total of 5 forces, or at least forces and components of forces, along the line of action. Right now, I'd like to take some time to point out why m3g sine theta is along the line of action. Before we rotated our M3 block, if we had kept our force diagram the way it was, we would have the cosine component of M3G pointing in that direction and the sine component of M3G pointing in that direction. So this component is really that component there. So that is along the line of action, which is, in this case, pointing in that direction. So that's why M3G sine theta is one of our forces, or at least a component of one of our forces along the line of action. So our forces along the line of action equal we know that this has to be the total mass, because in step one, we identified our system. So for this situation in which we're using Newton's second law, we have to include from step one, all of the masses from step one. And these are all of the masses from step one. According to Newton's second law, all those masses are multiplied times acceleration. Now what we want to do is we want to look at the vertical vectors for M3. For M3, we have a normal force pointing upward. We've got the vertical component, or the cosine component, of M3G. And according to Newton's second law, that should equal M3 times acceleration. But because there is no movement along this vertical axis, this acceleration is 0, making M3A equal to 0. Let's also write out or look at the equation for the vertical for M5. There's only one equation for M5 because it has no horizontal components. No horizontal vectors. The only vectors are in the vertical, which are Ft and M5G. So we've got M5G and Ft, and according to Newton's second law, that's going to equal M5A. Now we need to be careful. Sometimes students are tempted, because they see two forces pointing in opposite directions, to make this acceleration equal to 0. That's why the motion map in the vertical is so important. If we look at the motion map in the vertical, notice that our acceleration is not 0. So we have to keep M5A and not make it 0. Alright, now in step 6, we want to plug in our values and determine what things or what forces are positive or negative. If we look at the vertical forces of M3, which comes from this equation, like we said earlier, the acceleration is going to be 0. So I know that the normal force, Fn3, according to this equation, is going to equal m3 cosine theta. Now you might be concerned about the negative sign for that equation, but let's worry about that a little later. Now we also have to figure out what this kinetic frictional force is, because we will eventually have to plug in some variables right there in our main equation. Well, the kinetic frictional force, as we know, is always equal to mu sub k times a normal force. In this case, because we're looking at mass 3, that is our equation for the kinetic frictional force for mass 3. It's mu sub k times the normal force, that force, of mass 3. So let's combine these equations. Let's take this normal force and plug it into there, and what we'll find is that our kinetic frictional force becomes this new equation there, where it's mu sub k times m3 times g cosine theta. Now what we can do is we can take our equation from earlier and make sure we've got all the correct variables substituted into that equation with the correct positive and negative signs. So this is where it's really important to make sure we know the correct directions. So M5G is in this direction. So M5G, we decided, is along the positive line of action. So we'll keep M5G positive. This force of tension points this way along the line of action. So it's going opposite our line of action. So that's why we have a negative sign for that tension. Now this tension here along our line of action is in the positive direction. So that's a positive Ft. Now let's look at our kinetic frictional force. Our kinetic frictional force is getting substituted right there into our equation. If we go back and look at our kinetic frictional force along our line of action, it would point in this direction, which is in a negative direction. Finally, let's look at our other component, our horizontal component of M3G. It's along the negative line of action. It would actually, if I were to draw it here, it would point in this direction before I rotate it. So let's look at the force diagram before I rotated it. It would actually point in that direction, which is the negative direction for our line of action. We write out the rest of Newton's second law, which is taking the mass and multiplying it times acceleration. Remember, we're using both masses because we're looking at the entire system, both M3 and M5. At this point, we can do some straightforward algebra. We notice that our negative Ft and our positive Ft cancel each other out. And solving this equation for the acceleration gives us this expression here. That's actually the answer for our question when it asked us to derive the acceleration. Our problem also asks us to determine the tension in the string. So in this case, let's look at just one of the two blocks. Of the two blocks, now let's solve for the tension in the string. Now when we solve for the tension of the string, we want to look at just one of the two masses, not the entire system, because as we saw earlier, if we take the entire system, the forces of tension will cancel. So let's choose one of our two force diagrams. Of those two force diagrams, it looks as if though this is the simpler of the two force diagrams. So let's use that force diagram to calculate out our force of tension. So we wrote this equation earlier, but we didn't include the positive and negative signs. So what we'll do is we'll rewrite it down here and make sure we've got the right positives and negative signs. So once again, along our line of action, when we're going downward, we've got a positive M5G, so we're going to leave that positive. The force of tension that points in this direction is negative. It is opposite the line of action, so we'll leave that in as negative. And because now we're looking at just one of the masses, and in this case specifically M5, we will only put M5 into our equation for Newton's second law. A little mathematical or algebraic manipulation, solving for F sub t gives M5 times G minus A, and then we'll substitute we already solved acceleration as being this value. If we plug it into there, then we get this as our equation for the force of tension.